at Cosmology from about lensing of gravitational waves and some applications to fundamental physics. First of all, let me explain why I think lensing of gravitational waves is a very interesting and promising field. First of all, there's the indisputable fact that lensing of electromagnetic radiation is a fundamental test of many aspects of the universe, in cosmology, in astrophysics, and also in fundamental physics, such as the identification and probing the properties of dark matter. But lensing of gravitational waves is not just more of the same. Gravitational waves are very different and also very complementary. One aspect that will be the main theme of my talk is the fact that their coherence and low frequency allow the observation of wave effects. The frequency of gravitational waves is orders of magnitude lower than the longest waves that can penetrate the atmosphere in the electromagnetic spectrum. Gravitational waves are also weakly coupled, so we can see them travel from any environment, no matter how opaque or dense. And most importantly, gravitational waves are described by first principles. We can use the theory of general relativity to predict what the waveform is given the properties of the source. And this, when it comes to lensing, this can help us identify the events that are lensed. This is something that is very difficult to do with electromagnetic observations. And finally, gravitational waves are now routinely detected. This plot shows number of detections. We're here at about 100, and this is gonna skyrocket as the detectors get upgraded in the coming years. Now, when it comes to lensing, lensing is a rare process, but thanks to the increasing numbers, we expect a detection in the next, not in the current, but in the next observing run for binary black holes, and later on that observing run, we might even get a detection of lensing for binary neutron stars, which would be very interesting. So I promised fundamental physics, but I only have 18 minutes, so I'm gonna focus on dark matter. I think it's we can all agree it's a very interesting problem, whatever that is. And in fact, we don't know what it is. It could be vastly different things, from primordial black holes to ultralight particles with wave interference phenomena. And what's interesting is that most of these models and theories predict phenomena that we can observe with lensing. And in particular, I'm going to focus on compact structures or compact objects. This could be clusters of black holes, this could be collapsed subhalos as predicted by self-interacting dark matter, or this could be the axionic mini halos or the solitonic cores that form in wave dark matter. What's interesting is, and just to start, when we think about compact objects, I'm going to be showing this diagram that presents the abundance as a function of the object mass. The white areas are allowed. Colors represent current constraints. Gravitational waves are here. These are lensing only constraints. There are other dynamical constraints that I'm not showing. Gravitational waves are here, and for certain models, in particular for primordial black holes, we can have more stringent limits like CMB, which go around, gets very constraining, but this relies on the compact objects being black holes. They will not apply for extended objects. So another thing before I dive into is with gravitational wave lensing. So in gravitational lensing, with light, we're always in the geometric optics regime. The frequency is very large compared to the scales of the lens. And in this regime, we can distinguish between single image or weak lensing, when there are some more or less subtle distortions of the source. We can sometimes observe multiple images, and this is now done routinely. This is often called a strong lensing. And in the most extreme, we might even observe multiple trajectories of the light rays around the lens. This is kind of what we need to do to interpret black hole imaging and Event Horizon Telescope. But there's another axis besides the offset between the the lens and the source, which is the frequency. And this is very important for gravitational waves because it will allow us to explore this whole wave optics region here. And to be a little bit more precise, let's characterize when we talk about the offset or the angular offset, everything we tend to give in units of the Einstein angle. And when we talk about frequency, we can define a similar quantity that is the dimensionless frequency. It's the frequency of the signal, in this case a gravitational wave, multiplied by the mass. So you can think of this of the number of cycles that it takes to the wave to go through the not the lens itself, because the lens is big, but the gravitational radius of the lens. So this sort of quantifies phase differences associated to lensing. And the other quantity that's important is the amplification factor, which is just the ratio of the lens and the unlensed waveform in the Fourier domain. Now, here we can look at a waveform that is lensed. The blue one is a LISA source of a massive black hole binary. You can hear the in spiral, merger, and ring down. And if a certain lens luckily appears along the line of sight, we could see this wave optics phenomena that I will describe in more detail later. As I said, everything is characterized by the amplification factor. Amplification factor looks like this, the black curve here. It goes from 1 at very low frequencies to this rapidly or seemingly rapidly oscillating pattern here. And it's something that's very difficult to compute. I will not talk about how to compute it. You can ask me later. This is something that my group has spent quite some time doing. And the good news is that we'll soon, hopefully in a couple of months, have a publicly available code that everyone can use. So now let's dive into it. Let me start by focusing on strong lensing when multiple images form. So the usual picture of strong lensing is there are multiple images go around the lens. We think of electromagnetic radiation as separating these images in space, like resolving them with a telescope. But in gravitational waves, sky localization is very bad, so we do not do that. Instead, we resolve the images in time. So if we're here in this region of high dimensionless frequency and the amplification factor, this oscillatory pattern, if we go back to the time domain, is just the superposition of two independent images. You can see here, this is for a typical LIGO source with lens mass of 30,000 solar masses. And for this particular mass and configuration, the time delay is of the order of a second. And you can see that the copies can be brighter or fainter than the original image. Now let's make the lens lighter. This is a 300 solar mass lens. It's right in the middle of this diagram. And what you observe is that there are no separate images, but there is a modulation of the main signal, which is something we could in principle detect. And in fact, we might be able to detect this very easily if such a lens happens to be on the way. Now let's go deeper here. You can see that this amplification factor goes to 1. This is just the fact that a wave does not bother about something that's smaller than its wavelength. But if we're not at zero frequency, we might still be able to observe a subtle modulation with the frequency, which I'm showing here. This is for a 3 solar mass lens. So when it comes to lensing of gravitational waves, going back to the issue of compact dark matter, our current limits are here from analyzing these effects. In the future, by the end of LIGO at design sensitivity, 1 year, we could improve current limits by an order of magnitude. And I believe these are, I didn't do these limits, but I believe they are quite conservative regarding the source population. But most interestingly, perhaps, is that in the not so far future, in 10, maybe 15 years, the next generation of detectors, like the Einstein telescope, will improve 4 orders of magnitude in sensitivity. And this is a vast space for discovery. Now, Let me now tell you a little bit about the single image or weak lensing regime where we meet wave optics. And this is a regime where normally in geometric optics, we would just see one image, and with gravitational waves, there would be no distortion of that image, so we cannot do anything. But thanks to wave optics, there's a hope to observe in this regime. So here I'm showing this is the density of a lens. This is the amplification factor, and you can see that it oscillates, but instead of staying constant, it has a damped oscillations. And here I'm showing the Green's function. That's the Fourier transform of f. And the Green's function will give you the lens waveform in the time domain as a convolution. And what's interesting is that it shows a peak at the center of the lens. Now I'm going to separate the lens and the source farther and farther. And what happens is that this peak moves. Here I'm rescaling by the impact parameter, dimensionless. So this peak moves, and lowers in amplitude, as one would expect. But these little wiggles might still be observable if we have a very loud signal, for example, in the case of LISA. And because weak lensing is much more common than strong lensing, this might be easier to observe. Something very neat about this Green function interpretation is that if we have composite lenses with multiple pieces, each of the sub-lenses will lead to its very own peak. And this is not very clear to distinguish in the frequency domain, but it appears transparently in the time domain. So we can increase the number of lenses. Nothing prevents us from, at fixed density, nothing prevents us from going to a larger number. And we see also that this approaches the green curve, which is the average lens. Now, let me just, in the minutes that I have left, talk about a different effect, which is more at relatively high frequency, so it's not wave optics, but it includes strong and weak lensing in a stochastic manner. So let's imagine that we have compact objects in the universe, and I'm going to be working in geometric optics, so there will always be a main image. And there's this interesting property that compact objects always produce, each compact object produce at least another image of a source, which are described here by this. Each image has a magnification and a time delay. And these images, these compact objects will exist, few or many, and they will be at a certain angular separation from the lens. So here I'm showing a specific realization. These are the crosses are the images, dots are the lenses. These images are very close to the lens, and they're usually very demagnified. The magnification here appears in the color, and you can see the distribution on the right. This is dots are assuming isolated lens approximation. Crosses are solving the full system. So we can increase the density of lenses. This is the density of lenses, dimensionless, and you can see that this isolated lens approximation is reasonable. If we increase the density of lenses even further, this isolated lens approximation is actually very conservative, because the clustering of lenses enhances the intensity, the amplitude of these signals. So an idea is, which I elaborated in this paper, is if there are compact objects, can we distinguish these signals collectively on the waveform? And what this would look like is we would have, here is the strain as a function of time. The black line is a main signal, and then all these secondary signals would appear at a later time. Each peak is a copy of the waveform. It's a phase-shifted copy of the waveform. And you can see that the amplitude is lower, but there are also many. And also, I'm showing this dotted line is the average amplitude of this signal. This would be if all the lenses are 10 to the 4 solar masses. Of course, the time delay is proportional to the mass of the lens. So if we consider heavier lenses, this, instead of being of order a minute after the main signal, we would be talking about hours or even days. And this is something that we could, in principle, it carries signal, it carries information about compact objects, and we can try to find in the data. So what I did was quantify the signal and compare to other limits. And if we include lens stochastic diffraction, we can gain an order of magnitude, particularly for high masses. At intermediate masses, this doesn't work by construction because I'm only considering geometric optics images that can be treated separately. So at intermediate masses, these single image analysis are more powerful. Perhaps the stochastic framework could be improved, but at high masses, we gain an order of magnitude. And this is simply because we are putting more information in the signal. So if we can extract it, we could be very sensitive to the abundance of compact objects. And very interestingly, future next generation detectors might allow us to even find supermassive black holes if their abundance is as given by quasar luminosity studies. That would be around 10 to the minus 5. Now, before I wrap up, let me just mention that in the strong field regime, there are some interesting effects. So I've talked mainly about diffraction, but strong gravitational fields will also produce this dispersion, so frequency-dependent propagation, and birefringent, that is polarization-dependent propagation. There's also another case to be made that we can use these effects to study theories beyond general relativity. In that case, we don't need strong gravitational fields to do that. Also, if you're interested in these topics, we have an upcoming workshop in Vienna in December. You are free to check out the website and get in touch with me if you want more information. And that's basically it. Let me conclude with my main points. Basically, I hope I convinced you that gravitational wave lensing is very complementary to electromagnetic observations. Strong lensing is spectacular and very informative, but it's also infrequent. And on the contrary, weak lensing is subtle, but very likely. And this includes this stochastic diffraction phenomena that I described. In terms of fundamental physics, I focused on compact dark matter, but there are lots of other applications that we've presented, other people have investigated, and we are still developing. Feel free to ask me about it. And also test gravity and dark energy theories.